Let's now look at the computational efficiency of KNN. So, like we said, in terms of training, the complexity is basically to store. So we have a big ON in terms of big O notation, complexity in time and memory. We need just to go over all that data set and to store all this data set. And when we want to do classification, when we want to test, evaluate the class of samples, we need to get the k neighbors. So we need to get the k closest neighbors of X in the training set. With a naive algorithm, that is for each data to classify, we have a complexity of big O n log n, because we need to loop over all the samples, all the training samples, and we need to keep or to define whether or not they are the closest ones. So the log n part is really to get the kind of rank or obtain the k lowest or the distance values according to our training set. And as such, if we want to classify m data samples, the complexity in time is big O m times n log n. So we are mn log n, which is relatively big, because if we have many samples to classify, if we have as much test data than we have trained data, we are at something that is around n squared log n. So that complexity is higher. So even with, I would say, if the training is at no cost with KNN, we are paying a cost in terms of testing. So the testing of KNN can be quite costful, especially for big training sets, because then we have to compute the neighborhood, the distance with many samples and get the k closest samples from that. So it can be an issue, and KNN is not dealing well with really big data sets. But these are naive approaches. We can implement more fancy, more sophisticated approaches to apply KNN over bigger data sets. A way to do that is to make use of specialized data structures that will allow us to get computations to be more efficient. So we have things like the KD tree. It's not the only one. We have other things like ball trees or whatever, but I will present you today the KD tree, which is a data structure specifically interesting for computing the neighbors of some samples according to Euclidean distance, for example. So it will structure the data in the space in such a way that the computing the k nearest neighbors will be much more efficient. So the point with KD trees is that we want to avoid, if we are computing the distance with some samples, after computing some distance, we basically know that maybe a bunch of samples that for which we haven't computed the neighbors will certainly not be the nearest one to our current samples, because they are already quite far away from the data over which we tested. So we are sure that they will not be closer to our sample than what, according to what we have computed so far. So it's really a way to avoid, to take into account the structure of the data in the space and to focus only in the space where we know our data is lying and where we know the nearest neighbors are located. So this is making a structure of that space with the tree-like data structure. So it is capturing the data topology using an Euclidean space. That means that the basic KD tree, possibly there are some variations that are going beyond that, but basically the basic KD tree is assuming an Euclidean space. So assuming that we are using an Euclidean distance. So using an Euclidean distance, we are building a tree that is structuring the training set in some ways, such that when we will test some samples for getting the k nearest neighbors, we will not compute distance over all the training set. We will compute it only over some elements of the tree. But to be able to make use of KD tree, we need at first to build up that KD tree. So there is a cost of building up the KD tree. It's basically like a training algorithm, but we are not training, we are building the structure. And this construction of the KD tree over a training set of or data set of n samples is n log n. So this is n log n to build up our coded tree, and we need to store it into memory. So basically it's n, so proportional to the number of samples. Now, once we have the coded tree built, we can query the k nearest neighbors of some samples, and this is of a complexity in d dimension of n power d minus 1 over d plus k. So still it is less, it is sublinear, but you know, with big D, it is kind of really close to be linear. But at least it is not n log n, it is slightly below n. In 2D, this is nice because we have, well, this is the same result, but basically for 2 dimensions, it is square root of n plus k. So in 2D, it's super efficient. And in with one neighbor, it is even more efficient. So with k equal to 1, the query is log n directly. So if we want to know what is the nearest neighbor of that sample, we need to go down the tree basically and figure out, according to our data structure, the point where we have the nearest neighbor. So if we are processing a test set of m samples, the complexity is still in big O notation, is m times n power d minus 1 over d. So it's slightly below n plus k. K is the number of neighbors that we want to obtain. So this is kind of relatively fancy, and we don't usually want to implement it by ourselves because there is many edge cases, and in terms of numerical stability, efficiency can be relatively tricky, but there are efficient implementation of coded trees available out there. For example, in C++, we have Seagull, and we have like similar things in scikit, in SciPy in Python with scipy.spatial.coded tree. We have an implementation of that is kind of efficient and tested. So it's easy to make use of it to get a more efficient implementation of k-nearest classification, for example. We want to illustrate how the coded tree is working here. Let's assume that we have these samples A, B, C, D, E, F, G. So we have 1, 2, 3, 4, 5, 6, 7 samples. And what we are doing is that we are building up the tree on the right. So the tree is basically that thing. So we have 7 nodes, which are corresponding to our samples. So at the root, we have A here. And in fact, A is splitting the space like that here. So we are splitting here. On the left, we go to B here. And from that, we have D and E, which are the leaf of that subtree. Likewise, we are splitting it that way with A. On the right, we have C here, which is also splitting it that way. And then we have F on one side and G on the other side. So we can see here basically that we have this region that is corresponding to D, that region corresponding to E, that one to F, and that one to G. And the non-leaf points are the samples used for making a split according to one dimension. So we have B and C here that are making the split according to the horizontal dimension, and A is making the split according to the other dimension. So if we have here that sample, we want to classify that thing here. We want to get it classified, or to get the neighbors. In fact, to be more precise, we want to get the neighbors here. So we want the NN distance. So basically, it will be based on B. So I think that here B is the closest one, and we see that sphere correspond to the sphere at the same distance than B from that sample. At first, we start with A, and we know the distance between our point and E here. And from that, we have this big ball. This big ball is telling us, okay, we know that A is at that distance in terms of nearest neighbor. So we go into a depth first. So then we will examine the left child node first. So we have this with A, and then let's move with B. So with B here, we see that we are reducing the ball to that thing here. And we compare this with the best estimate, which was A before. And we see that B is closer to the point than A. So let's keep B. We will not go back at A. And then we will evaluate the distance to D and E, and we can discard them because we see that in fact B is the closest one. And then we can just proceed back. Wait, and then look at the right side of A, but directly we know that this right side doesn't need to be looked at because these are kind of far away. They are further away from the distance we have to B, so we will not keep them. So we don't go on the right side here. It is not required. And we keep as best estimate B. So B here is the nearest neighbor according to that search. And that search implied just to go down on the left side of A. In fact, we don't even go with D and E. We are able to just say, okay, B is the best one, and that's it. Just give you the intuition of that approach. And in scikit-learn, this is implemented. This is a way to make use of k-nearest classification efficiently based on KD trees or other data structure.